So we see and hear you well.
Thanks. All 10 of you, I suppose. Okay. Okay, sorry, being late. I'm in a huge rush today from class to class. And there is another one. Okay, so we're running a little late on the schedule because of slow classes and because of all of the transitions and shifts in the schedule, especially of the practice sessions. After today's class, sometime this week, I cannot guarantee when exactly, but I can guarantee that this week for sure you will get finally something asynchronous. I know that you've been asking about getting asynchronous materials for self-study, but I should have mentioned that this course initially, it was not supposed to have any asynchronous materials, unlike Econometrics that we had last year. So the asynchronous part for this course is the online course on EDX that you are supposed to study on your own. So anyhow, because we are running a little late, a part of the lecture on ARIMA models, I will record for you. That why ARIMA? Because we have to go through it, and why asynchronous? Because you have the online course where you cover it pretty well, but we need some updates on how to make it like a little bit more practical. The suggestions that they have. Just a second, I'm sorry, I'm seeing some lags in my camera work. I will reload briefly and we'll be back in 5 seconds or 10. Okay, it should be better now. Yeah, and I forgot to start recording anyway. So hi again, once again, everyone. So a part of asynchronous materials is coming sometime later this week. So far, we have to finish what we started about the stationary transformations. Please, could someone update me on how far did how far you got in the practice sessions? What did you cover last with Polina? If any of you visit the classes, attend the classes at all.
We compare the results of KPSS and ADF tests.
So unit root and stationarity testings. Have you started at all transformations? I know that you've been discussing that at least a little bit, but even before. But in the last class?
Yes.
Transformations.
What kind of transformations?
Heavily discussed разностные, относительные.
Differencing, yes, okay. Разности is differences, like literally difference. So, and yeah, the other one we will see what you mean by that. Okay, so we will finish that hopefully today, all of it, and probably even maybe start something new, but I wouldn't count on it, honestly. If it wasn't for the econometrics makeup exams that are going on for the 3 weeks already now, it would be better, but okay. So this is where we approximately where we finished. It's like a little recall from the purposes of stationary transformation. So when we are talking about stationary transformations, we basically change our data so that they would look stationary, or because we don't have like enough information, or almost never we have enough information to state that a time series is definitely stationary. We might have some intuition or like theory basis for it, as usually in econometrics and applied econometric analysis. So that also applies here. And the type of transformation that we should use depends on the type of non-stationarity, as we talked last time. So if your time series is linear, it should be one linear trend. It should be one kind of transformation. If there is explosive trend, there should be something else. Depending on the kind of growth or kind of decline, there are different transformations and so on. But this is all about trending and like stable changes over time. Some kind of changes are stable, even though the time series, original time series itself is not stable. That is something like rough explanation of non-stationarity. Some kind of changes should be stable. So when we see a linear trend, we understand that, yeah, okay, so the changes that appear over time, like in absolute, not in absolute value, but in the levels, change in the levels, it looks somewhat stable. Like it approximately grows the same amount of units every period of time. Like every year or every 10 years, on average, it's the same. So it gives us the hint that if we take the differences between like the sequent observations, so like so that there's the same time period between the observations which we are differencing, we might get something stable. If there is something like exponential trend, we might take logarithms, for example, and then take the differences, and then we would get more or less stable something, or switch to percentage growth. That would be the same, and so on. But such things are as structural breaks, for example, no matter how much we take differences or do other transformations, we are very unlikely to be able to get rid of structural breaks. If we see structural break in the original time series, it will remain there also in the differences, in percentage changes, in whatever. It will look differently, but it will be still a structural break, or at least as an outlier, depends on how fast it happens. But many structural breaks don't happen like overnight or like within one observation, if it's even if it's annual data, right, on a yearly scale, then it might take some time, like a few years or like a few days, even if it's daily data and so on. And then when we do the transformations, it will still be there, like some kind of outlier, and it will, well, it will not be very good for our modeling, for the quality of the estimates and so on, for the quality of predictions, and that's one of the major reasons to use univariate modeling to begin with. So that's not good. So those things are dealt usually within modeling already. So when we deal with the time series that is stationary otherwise than having some structural break or some heteroscedasticity, we can deal with that. We can still model it as if it was stationary or like almost stationary, but control for those structural breaks. For example, like by including dummies or maybe correcting sampling scheme such so that the structural break is off. To include a model for the variance, not only for the mean level, and then deal with the heteroscedasticity and so on. So that's already a part of modeling. That's why all of the transformations, they deal with the like trending behavior of the data trend in mean, so on in the average level. That we do before we start modeling, and then we switch to the modeling. So detrending transformations, that the kind that we do prior to modeling, there are many of them, and to each time series that is non-stationary, we can find several alternative options of how to transform the time series so that it looks stationary, or so that we can confirm from the testing that it is stationary. The problem is which one to use, and there is as usually no like one single answer, and that's why essential meaning of the transformation is crucial. Again, so unfortunately, even though econometrics uses a lot of mathematical statistics, probability, and other related mathematical results, studies, theories, and so on, essential meaning is very important. So yeah, there is Box-Jenkins methodology, for example, that says whatever time series you have, just use differences. If the first differences are not enough, take differences of the differences, hence the second differences. If that is still not enough, then take differences of differences of differences. If that's still not enough, well, then an economic intuition should say, like, take a hint. Differencing is probably not working, because the third differencing, what is the meaning of the third differences? If the first differences show how time series change over time, like from one observations to another, how much it grows or declines on average over time, that makes sense. If we are talking about second differences, it's already harder to interpret, and it's harder to find any meaning in that, but we can still somehow relate to that. So it's a kind of acceleration, how fast or how significantly the differences, the first differences change. So how fast changes the rates of the change of the original time series. It's already a little bit hard to imagine, but something like distinguishing between linear and quadratic function, right? So that's the difference between first differences and second differences. But third differences are okay. What is that? Why would it be stationary? So in it might be stationary because any kind of differencing can kill non-stationarity in everything, but it doesn't mean that it is a meaningful thing, and the transformation should be meaningful. Otherwise, the modeling will be a disaster. It will be close to impossible to interpret the model, and that's important. The models should deliver interpretable results, right? That's why in practice, you will almost never see differences higher than 2 in economic data. And for logged variables, you will not see differences higher than 1. So if you log data, normally if you log data, that's to apply first differences and done. That's it. Second differences of logs, that's something very hard to imagine. Third differences of anything is also very hard to imagine. It means that something is going wrong. There's something that we don't understand about the data. Probably it's just not appropriate to model it as a univariate time series. It should be modeled like jointly with something, so that we can explain by looking at some other data, some other variables, some other processes, some other events. We can explain why this time series at hand of our interest changes in this way, so that it is non-stationary. Oh, yeah. About the essential meaning, for example, compare the percentage changes and deviations from a trend. Deviations from the trend, it's something that we almost don't consider in our course, but well, pretty much just in this example, but you might see it in that online course as examples. Anyway, what it is, it should be pretty clear. Percentage changes we considered last time, and deviations from the trend is something like more long term, because to observe a trend, you need a long period of time from which you can even estimate or draw some conclusions about what the trend is, how the data is trending, how the series is trending, what is the long run behavior in towards the changes. And percentage change is something that happens very quickly. So we only observe from each data point, we only observe change in this current period relative to the previous one, and then to the previous and so on, right? And trends are showing long run behavior. And when we see a deviation from a trend, we can suggest something about deviations from a long run tendency somehow, but we probably cannot know why it happens. Whether it is a change of trend, we don't know, because to observe a change of trend, we need a long run future behavior to also observe that the trend changed. Maybe it's like a random shock result or something like that. Anyhow, to observe a trend, we need a long history, and we never observe a trend in the future. We don't know whether it is going to remain there, or it is going to like just be changed or disappear completely. Unfortunately, in some cases we can, but those happen not normally outside economic context. Sometimes in some fields, in some contexts, we can like rely on observing long run trends that don't change. Usually those are like very deterministic dynamics, like some kind of weather trends, really long and stable, but these days even those are, well, questionable. Maybe something like related to the movement of the planets in the sky and so on. But even those are reconsidered sometimes. But in economic analysis, detrending by taking deviations from a trend is to oh my god, no. Sorry, just a sec, I will fix it. Can you see the board now? Yeah, you should. Deviation from a trend. So imagine we observe time series like this. The frequency is not important. The meaning is also not so important now. So it's obviously increasing over time. There is some kind of trend. If we don't know what kind of trend, then we might just try to plot, what is that, a linear trend, which just shows linear growth over time. And the difference between the actual value of the time series at each point of time and the trend is the deviation from the trend. And so on. So it's easy to imagine. Unfortunately, it is only applicable in historical analysis and has no use in explanation, or it has no use in prediction or forecasting. So why so? Because to be able to even draw this trend like this, we have to observe all the history of this time series. So we can only judge about this trend only like at this point, maybe somewhere close to the end of the sample, starting from here. If you draw this, if you try to estimate the same trend over the first half of the sample, for example, to the left from this time period here, it might be a lot different. Something like this. A different slope, different rate, and different deviations, of course. And at what time the trend changes, we have no idea. Maybe the trend is not there at all. So before this change here in the middle, it might seem like there's no trend at all. And same goes for prediction, for example. We don't know whether the trend is going to stay there, this trend or not. So it's very unwise, immature, and, well, basically pretty much illiterate in terms of econometrics and statistics to try to do predictions based over deterministic trend. Like to assume that in the future, the data will still continue to like fluctuate around these tendencies that we estimated from the past. Because it wasn't in the previous, in the history. Only in this particular sample, there is this trend, and outside of it, it does not exist. So in some sense, the estimate of a time trend, deterministic time trend, is, well, it might be a good tool of descriptive analysis just to show that there was a particular tendency to grow or to decline or not to change on average during some particular period of time. For modeling and prediction, it is not a good tool, so we do not consider it. Anyhow, it might be used in some cases in long-run prediction, as I state here. But it happens very rarely and almost never in economic context. A very important type of transformation, that the one that you already mentioned, is разностные преобразования, difference transformation or differencing transformation, or just differencing sometimes. And log difference is very often used, not always, but very often. It is mostly applied, first of all, to financial kind of time series that are price related, volumes related, values related dynamics, and then macroeconomic, like GDPs, prices, imports, exports, and so on. So whatever, there are options what to use, either log differencing or percentage changes. It depends, of course, on the data. Log says that it's something related to taking logs of the data, so the data must be appropriate for taking logs, so positive almost surely, and so on. And the other type of transformation is the one that we already saw last time. Percentage change and very closely related, like very closely related, growth rates. They are just actually in a functional dependency between them. So it's like one change at all. Difference in transformation, like log differences, is just a special case of difference in transformation, because it's when you take logs of the data and then take differences. So it's like this. In my practice, which might have a little bit bias from my field of expertise, which is financial time series, these are the most commonly used. However, in macroeconomics, you will often see percentage changes in growth rates. In other kinds of fields of practical application, well, differencing is still very popular, but mostly because of the approaches to univariate prediction, the ARIMA models and related. In data analysis, that doesn't care much about like the domain, which is not really a good thing to do, not to care about the domain, that the context, the essential meaning. Like the first choice of something to do mechanically is either to use percentage growth or like percentage change, or differencing transformation as well. And if it doesn't work, then repeat it again, which is not always the best choice. And yeah, and they are all essentially based on difference transformations with some details. So differencing is the main kind of transformation that allows us to do detrending. Consider this example, please. Do you understand what the title says? What does it mean? What does this time series represent?
So those are the emissions of fumes in Morocco.
Yeah, so not only fumes, but other kind of emissions as well. It's probably some kind of estimate. We don't know how it is estimated. Probably there is some normative analysis behind it, not just statistical, like observation and so on, because it's hard to measure that kind of stuff. So yeah, CO2 emissions, that is carbon dioxide, right? Emissions, this is metrics very, well, not just closely related, but one of the main metrics of analysis related to climate change, energy consumption, and so on. Ecology. So yeah, in Morocco, why Morocco? No, well, why not? Because it was right there on Quandl, that time Quandl, now Nasdaq data. So on annual scale means that one data point a year, and MT, what is MT? How do you measure emissions of gas?
Cubic meters?
No.
Megatons.
Yes, it's megatons. I'm not sure if T should be capital or not, but I think it's correct. So yeah, it's megatons. That's a standard international unit for this kind of stuff. What do you think about the original time series? This one, that says levels. I'm not sure if it's all visible, but yeah, the first panel, the upper panel of the plot says levels, and the second one is first differences. What can we say about the original time series? There's also period stated, but also very small. I'm not sure if you can see it at all. It's from 1965 to 2018. The labels of the axis is not very smart. It always says December of December, 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 even though it's like just, it's always December because it's annual data. So a year alone would be enough. And even better, not so disturbing. The most important observations, given observation about the original time series, given the stuff that we are discussing now. Related both to essential stuff and visual analysis. So it's obviously trending on average. There's now no significant, no very strong signs of trending in heteroscedasticity in variance in the original series, because it's trending in mean, so we cannot discuss heteroscedasticity of the original series. But it's trending in mean on average. The average level grows substantially from period to period on average, and mostly every period there are sometimes short declines or like flats, but not often enough. So there's a trend. Does it look like a linear trend to you? What do you think? Yes, it does.
More exponential one.
Why? To both of you. So
To check, maybe we need to check both models for exponential, maybe for linear ones. I don't know exactly. I think we don't know how exponentially we can check.
How
Because
do you check linearity?
we can logarithm it.
No, but that would be checking for exponentiality exactly. But if you want to check if it resembles linear trend, linear tendency, how do you check it? This is what we discussed last time. Remember, what is the difference between exponential trend and the linear trend?
We need to take difference.
Take what?
Percentage change we need to take. If it
Yeah, but
is
percentage change we don't have here. What we have is first differences. The second panel is first differences of the series. Yeah, so to judge about the kind of trend, we need to apply different kinds of transformations. First of all, yes, essentially, it would be reasonable to assume that this kind of data could be, this kind of series could be exponentially growing. Also, visually, it resembles something very, maybe like a very, very flat kind of part of that exponent, of that power function. But there is something like there is some acceleration. You see it, like you can barely see it, but it's a little bit there. At least at the end, we see that there's definitely some acceleration related to the beginning. Maybe it's a structural change. Maybe it was just one linear trend and it changed. We don't know that. That all requires a lot of more essential information about what was happening there, like in early 90s. Here in the beginning, in the middle. Maybe it's something else. Maybe it's indeed exponential and then it was just growing faster. Then there was some extra volatility in the second half. And when we apply the transformation, the first differences, why do we apply first differences? We apply first differences if we want to switch to a stationary time series, assuming that the original time series is linearly trending. If a time series is linearly trending, then we have to take first differences and see what's going on. If we assume that it is exponentially trending, we have to check. We have to either take log differences, so to take logs and then differentiate, or to apply percentage change. Yes, you are right. So in this case, we decided, well, I decided to apply the first differences and see what's going on. So based on this first differences dynamics, do you think it like corresponds to the assumption about linearity of the trend? What would be the sign of linearity of the trend if you want to see it from the first differences dynamics?
The same first difference.
Yeah, it should be the same, roughly at least, right? So if the trend is perfectly linear, then the first differences are just a constant. In this case, positive. If this is a growing trend, then should be something positive. This. This is one time period. Because in case of exponential growth, we would see first differences also growing. If the time series is somehow like roughly trending linearly, but fluctuating on average around something that looks like linear trend. Again, this is just the linear trend. In this case, is just like in our imagination, in our mind, because it might not be there. Then the first differences also will be, on average, they will be stable around some constant, but there will be some fluctuation. That's almost like definition or like a rough definition or rough intuition for a stationary time series. So it's in mean. It's averaging around the same mean, not oscillating without like convergence or something. It tends to be there all the time. Sometimes it deviates more, sometimes it deviates less. Sometimes it stays above or below this for several periods, but on average, still it remains there. So what is the conclusion about this first difference? Does it look like it's stable over time, over some around some constant?
It doesn't,
Why doesn't it?
because on the second part, it has like a much bigger variance.
Yeah, variance is definitely bigger, but what about the mean level?
The mean level is pretty the same.
Yeah, to me it seems like okay. Most observations, even when we take the second part in account, most observations are somewhere between that 0 and 2 here in this like second uh, row of the plot. They fluctuate somehow a little bit, but on average they stay the same. There is some growth on average of the first difference in the second part because of those large deviations. There are also large in absolute value deviations to the downside, which would indicate declines, which happen very rarely. You see, we can now even see how many declines were there, like 1, 2, 3, 4, 5 months over like many years, 5 episodes of decline. Yeah. To proceed, we need more essential judgment, more essential information about it, like what would be our assumptions about linearity of this thing. Honestly, this is just a technical example. Honestly, I would start, if it was a real life analysis, I would start analyzing this thing or thing like this with the assumption of exponential growth. Why do you think that would be a more appropriate, essentially, to assume exponential growth of CO2 emissions?
We've just discussed that the first difference looks like the TS is linear, while the exponential.
Well, yeah, that's the problem. So that's going back a little bit. Essential information and essential judgment is crucial because sometimes we can suggest different kinds of transformations that would transform our original series to something that looks stationary. I'm not sure. Yeah, I don't have here the same plot for. I don't have here like a plot for exponential logarithmic transformation of this data, but I am sure that taking logs and taking differences or taking percentage change would also be quite stationary. Why not? It might be, and it might have a little bit less variance in the second part that happens. Maybe not. The question is about essential thinking, essential judgment about why a thing like that would be most likely exponential, even before seeing the plot. Okay, within this period of time, it looks linearly trending. First differences are okay, but there's no guarantee that it persists. And if we try to assume that this is the long run behavior of this time series, and we'll try to model it like this, and then draw predictions based on this assumption. And if the actual series is exponentially trending, we are in trouble. We are going basically to underestimate its growth. That's the main problem. So wrong assumptions lead to wrong conclusions. And if we're trying to predict, for example, this time series based on the linear dynamics when it's actually exponentially trending, our predictions suck. Not immediately, but like in a few years for sure.
So we are just sure that those emissions are growing exponentially, and we can even see it a little bit on the first graph,
But
right?
why would be sure? Because this is a common kind of judgment about particular kind of time series, particular kind of data that depends on like some essential thinking about them. Why would we assume something like that? Something like that to be exponentially growing? The answer is pretty much there already in the plot. Even though this is just mostly about visual analysis, there is also quite a lot of essential information. Well, basically, it's in the title, of course, because there is nothing else essential. If we didn't see the title, then we cannot do anything essential about it. It's just some trending data, whether it's exponential or linear, we don't know. Linearity seems like a reasonable assumption based on just the plots. But what about the meaning of this data, meaning of this time series? What do you think determines CO2 emissions in a country? There are not so many sources. This is like macroeconomic level of carbon dioxide emissions. What are the sources?
Factories, mainly.
Yeah, industry, heavy industry first. What else?
Farms.
Sorry, what?
Farming industry. I mean, farms and all this stuff.
Agriculture. Yes. I'm not sure about the state of agriculture in Morocco, but yes, definitely in general, yeah. So heavy industry, agriculture, animal agriculture, yeah, and well, yeah, all kind of agriculture actually, mostly animal, not only. What else?
Government.
Why?
Because of the policy of green life. I don't know.
Yeah, but what is the actual source of the actual emissions? That's the question at hand. Like the physical source. Well, there are also cars and other kinds of transport. They are partially related to the industry and agriculture, of course, because it's like the part of that production. But there's also final consumption of transport, just private consumption of transport, cars and stuff like that. And what do you think the level of those things depend on in the country, roughly speaking? Because we are talking about long time period now, over 50 years.
So, roughly speaking, the number of those polluting factors depend on the scale of the economy.
Yeah, on the economic growth, basically. If we're talking about how it changes, yes, stuff like that. They are very, very closely related to the growth of the economy, especially in the case of economies that are not like super well developed. There are no such thing as like indicator of a super well developed economy, but there are at least some economies in the world that we consider like developed economies, and some are like less developed or developing or emerging, whatever we call them. But this is like a little bit different kind of stage of economic development. it indicates that there's going to be quite extensive use of environment, probably quite big and also extensive growth of infrastructure. That means also transport and so on, stuff like that. Population growth also contributes, of course, to emissions indirectly through the demand to all of those things, to energy, to transport, to products of those industries that emit CO2 and so on. So these things are very, very closely related to economic growth, and economic growth in the world, in all kinds of economies on the long run, it is like almost like already a common knowledge nowadays in economic analysis. It is considered exponential, even though there are some structural changes from time to time, crises and so on long run, and 50 years for a developing economy is already a long run, especially if it's like the second half of the 20th century. It's definitely a long run. And Morocco is definitely a developing economy. It's not a too well-developed country. There are, of course, many factors that contribute to economic development, but on average, yeah, it's most likely economic, and it is reasonable to consider such things related to that. Of course, it's an assumption, and it might even be a hypothesis subject to analysis in the context of time series analysis. Even there might be a model that relates carbon dioxide emissions to the economic growth and other factors, and then maybe measuring the change, whether it's really related there, whether it's growing exponentially as economy develops, or maybe it changes to linear growth. Sometimes there might be even some kind of flat there, but that depends, of course, on the development of the economics and on the model. But generally speaking, over a long run in the history, yeah, well, exponentiality of the growth is a valid assumption. So we should do it on the first stage. If we don't have enough essential judgments, it's okay, because our job is mostly technical here. Assuming linearity is also okay. If it is wrong, we are going to see it in our in the quality of our predictions. First of all, as I said, if we proceed with this assumption of linearity further and continue predicting stuff as if they were trending linearly while they are trending exponentially, our predictions will show that pretty fast. If we have enough data and we run reasonable cross-validation analysis, we are also going to spot it, at least maybe get some hints about it. Okay, so that pretty a lot of time spent on that. So back to a little bit of mathematics. I'm sure you already know what a difference transformation is. Just to repeat it, if we observe and if we work with the time series, that is the original time series xt, then the difference in transformation is this. So this is just literally the difference between the current observation and the previous one. This is the basic difference. It always connects two consequent observations, current minus the previous one. This delta here, it stands like, it might be very unusual to observe it here. If you are familiar with notation for operators, then you can consider it as an operator. If not, then just look at it as if like some fancy kind of notation and consider this as a separate variable, like delta x is a separate variable of x. Actually, delta is a linear operator in the time space. If it tells nothing to you, it's okay. It's not subject of our course to cover operators, but I think most of you dealt with that somewhere in dynamic systems, I guess. I'm not sure. And then, of course, we can also consider higher order differences. As I said, if we can take first differences over time series, we can also take differences of the differences. And we are not going to write delta delta x in that case. It's not a mistake, nothing wrong with that, it's just ugly. So what we do this, differences of order p, or the pth difference, which is an ugly thing to say. But mostly we deal with like first differences or just differences, that is this, or second differences. So then we say that, so the order, the differences of order 2, that's it. So delta power p xt, and this is it. It's iterative. And of course, we can like apply it several times and see, and can even derive like a formula for second differences, for third differences, but it's not that important, and it's pretty obvious. So if the first differences are this, and second differences are basically this, sorry. It's a linear operator. So it, when you apply it to a summation of time series or difference time series, you can just open up the brackets, the parentheses. And that's it. That's just substitution. Done. And that's second differences. Already not a really intuitive thing. So just looking at this expression, it is hard to maybe imagine what it means. And this is rather more intuitive. So when it's differences of differences, we understand what it means. If first differences show the differences of the original time series, then the differences of the differences show the acceleration of the original time series. Like really quick question. So if we observe, for example, second differences behaving like stationary process around some positive constant, delta 2. What would be the original time series? Approximately.
So we only know that it will change with the same speed. So like
with, yes, obviously. Acceleration, yeah, the acceleration is going to be the same, yes.
So it can be just a trend, maybe
yeah, what kind of trend? That's the question. You're right.
Trend may be either increasing or decreasing, but we know that if this trend is increasing, the speed of increase will increase. But if it is decreasing trend, the speed of decreasing will be
the speed stays the same. So it's
acceleration.
stationary.
The speed in this case is the speed is the first differences, something like that. Or the speed of the first differences, if you mean so the acceleration is a good term. But what kind of trend? So we know that, just recall that you just saw it. there is some first differences that behave like this. Then the original series is what?
Exponential growth.
Why exponential? No, not exponential. For exponential growth, we saw that it should be something else. For exponential growth, first differences are also exponentially growing, or at least just growing. That's for sure. Because when there's exponential growth, the growth over this period of time here and of the same period of time here are a lot different, right? It's growing. And then over the same time period, it's even bigger. It's somewhere there, a lot bigger. So the first differences will also grow.
Okay, I messed it with a percentage change, I guess.
Yeah, so it's not percentage change, it's the first difference, yes.
So in this case, it will be linear.
Yeah, something like that. And positively growing linearly, increasing, because this guy is positive. Not only just positive, not just growing, but always growing, right? So there won't be periods of decline because all of the first differences are positive, right? So there will be growing all the time. Yeah, I'm drawing it incorrectly already. I'm kind of, yeah, that again, some declines, there's no declines. This is just a very schematic thing, and this is of course not the correct trend. Something like that. Again, there are some declines that should not be there, but okay. So, and getting back here, okay. So the second difference is constant, means that the first difference is trending. It's always positive. It's growing. What it means for the original time series. Because this step here was from first differences to the second, to the original time series. For the second differences, the original time series is the first differences, if we consider just one differencing step. What is then the original time series behavior? So it changed, for example, here there was some difference, delta 1, then it was delta 2, which is a lot higher. So here it was changing with this. Differencing, that's the vertical.
Will it be the
And somewhere here it
exponents?
should be already higher.
Will it be the exponents?
Yeah, it looks like it, but actually not. Visually, when we start from observing the original time series, we will not be able to tell unless we do some essential thinking and analysis of the differences and so on. But when we start from like this imaginary example, we can tell for sure that this thing would be quadratic. So differencing, it's not just called like that. It's not exponential. It's quadratic. Quote marks because it's some quadratic function of time, of course, on average. And of course, there will be something, again, something like always growing, no declines, because the first differences are always positive.
Why quadratic? Why not cubic?
Yeah, because if it was cubic, always growing, then the first differences would be positive and quadratic. The second differences would be positive and linearly growing, and the third differences would be stable around constant. So differencing time series is kind of taking the derivative. See, this is like the discrete kind of a derivative over time in discrete time. Well, we work in discrete time. So how it changes over time. Taking the first difference is like the first derivative. When your time series was linearly trending, you take the first differences, and the first differences are constant. If your time series was quadratic, you take first differences, they are linear, the second one are constant. The third would be 0 on average. And of course, the fourth are 0 and so on. So it makes no sense already. And again, if you start with something that is not 0 on average, but stable over some constant, and its second differences, it means that the first differences were linearly trending, the second would be quadratic, because you upgrade the power one by one. So the opposite transformation, the inverse transformation, is kind of integrating. When you integrate a constant, you receive a linear function. When you integrate linear function, you receive quadratic function. That's the idea of differencing. It's like very rough, but it works exactly like that. Also in the practical analysis. So if you see a time series and you cannot choose what kind of transformation is the best, you can analyze not only just the first differences, but several orders of differencing and see what fits best. Because if it's not exponential, then some kind of differences will kill the non-stationarity completely. The differences should be stable around 0 at some point, because you differentiate. If you differentiate an exponential trend, you will not be able to get rid of it as easily. If you differentiate an exponential trend, what you receive as the first derivative of the exponential function.
So for exponential trends, we shall use log difference, right?
Well, yeah, that's an option, but that depends on what you if you believe that it is really exponential. Because in data, you cannot distinguish, unfortunately, between quadratic trend and exponential. So when you see something that looks like quadratic trend on exponential, and you have very strong evidence that it is quadratic trend, for example, there's no model, theoretical model that assumes that it is quadratic, then it's safer to assume that it is exponential. This is just common practice. But back to the question, what would be the differentiation of exponential trend? This is just a normal difference now. Or normal derivative.
So
with time.
It will be itself?
Yeah, it will not change, yes. So unlike power functions, like polynomials, like quadratic functions and stuff, when you differentiate quadratic function, you will decrease the order. When you differentiate exponential function, the order will not be decreased. So if you have a time series that is trending like explosively in some sense, like this, is it quadratic or is it exponential? The judgment should be made based on the essential analysis. That's the crucial, of course. But if you cannot, then how should you do? You can consider the first differencing, or maybe the second differencing, but that might be that's not delta. That's just the original time series. If it's still trending kind of like in resembling power function or something that resembles exponential, then it's exponential. If it clearly transforms to something linear, and it means that when you consider second differences of that, you will get a constant. And here you will get something that will still might be like this. It might already look like something linear. Or maybe something like even that depends on the data, close to constant, but not quite it after second differencing. Then it's a clear sign that the original series is better to consider it as exponential. If the order of that trend is decreasing, definitely decreasing when you take the difference, then it's probably better to keep the assumption of polynomial growth, not polynomial means quadratic in this case.
And
maybe cubic, why not?
But in the perfect world, the exponential trend shall remain exponential.
Yes, yes. In the perfect world, yes, but in data, unfortunately, no, because the samples are finite, sometimes even very short. And well, if you take the data such as GDP or like financial assets prices and so on, then exponential trend is pretty obvious, even when you have all the crises and other structural changes behind it, like economic policy changes and so on. But other things we don't know. So that's why we are saying that the essential judgment is important, is crucial, because from the data, it's too ambiguous. You cannot say often. Sometimes you transform and you will see something like this, even for something that is clearly exponential. Why? Because the data is not always not behaving like that. It will be something this. And will you be able to tell the difference between a trend like that, for example, if it's a short sample, and a trend like this, whether one of them is exponential, one is linear? This one probably resembles more exponential because of there's some convexity here that seems, but is it the feature of the data in the long run, or is it just because there was some declines and then rapid growth that could be random within some short period of time? If you remove this period, then the trend is linear. So from the data, it is very hard to tell. But sometimes it can be distinguished following this scheme. But this means probably when you observe the case like this, it's usually also that you can tell it from the essential analysis to begin with. That's why essential analysis first, then all the kinds of manipulations. Okay, so we have not much time, unfortunately. Another important example, probably the last one that we are going to consider today, and not sure about the log difference. So imagine that the original time series is as it is, as presented, and then we took the first differences. Doesn't matter why, it's simulated data, so essentially we don't know anything about it. Well, I know because I simulated it, so I know what kind of process it came from. And the trend in this case is actually linear. So the data generating process, the true population data generating process, was with a linear trend. However, the visual analysis might say differently. But yeah, that's why we do a lot more than just visual analysis. And the red line in the plot, do you see the red line in the second plot? It corresponds to the average level of the first differences. So it was positive on average. Now you don't have to think much, but this is a very important question. In the situation like this, so the first differences are positive on average. That means the sample mean of the first difference series is positive, does it guarantee that the levels of the original time series grew, that it was increased over the period? We know that when the first differences are always positive, the original time series of course grew. It was growing all the time. It was growing every time period. It was growth, and growth, on average around the same, sometimes small, sometimes larger, but always growth. But now what we see, I will switch back. What we see is sometimes there were declines, negative differences. Sometimes there were growth, sometimes even very strong growth. But on average, the first differences are positive. Does it guarantee that the original series grew?
It just guarantees that the original series on average grew.
What do you mean on average?
So
yeah, grew on average. That is the average of the first differences. So yeah, we know that.
So it doesn't guarantee it.
Grew over the period means to compare the endpoints in the beginning and at the end. Does it guarantee that the endpoint at the time period of the original time series was higher than the initial one? So you think it doesn't guarantee it?
No. I just misunderstood the question.
No, I'm just asking.
Yeah. So in that case, it guarantees, because if the mean growth is positive, that means that over the whole period, the growth should be positive as well.
So this is what we have, right? The condition, the sample mean of some growth is what this is, this thing. This is the in time series we use capital T as the sample size instead of n, and small t for the observations. This, and if we now plug in the definition of the first differencing, and just expand the summation. Well, it should be starting actually from 2, but it doesn't matter now. So imagine that we have observations from 0. We are in Python. Then t plus 1, but whatever. So the first summoned here would be x1 minus x0. Then the second difference between the second and the first, third and the second, and so on, between t and t minus 1. And now look at those. And so on. So what do we have in the end here?
A positive value.
Yeah, which ones are going to remain? So you see that this guy and this, they cancel out from the first difference, and from the first observation of the first difference, and from the second observation of the first difference. Then these are also, they cancel out, and so on. This also will be canceled out with something here. Which ones are not going to be canceled out?
X0 and x t minus 1.
Xt minus 1 will be here in this. right?
Yeah.
So they will also cancel out. But xt, no, because we don't have xt plus 1 minus xt. This is not here. It's already not in the sample. So this remains. And we don't have this, also not in the sample. So these remain. And we have at the end the difference over the whole period. And yeah. So yeah, this is just by construction of what first differences. When the first differences are on average positive, then the original series grew over the whole time period. So in the end point, it was higher than in the start, at the start, right? And also it shows that the importance that the differencing transformations are additive. You can sum them up over the periods. For example, if you have sequent observations of like delta x like 2, delta x 1, you sum them up and you get what? This, right? The change, like the difference over the whole period, because this shows the change between periods 1 and 0, this between 2 and 1. So from 0 to 1, from 1 to 2, you sum them up, you get the whole difference. That's the additiveness of the transformations. The difference in transformations are all the additive, unlike some others. Again, just some simulated data. Now imagine that we have the same kind of differencing, like we start not from the levels data, but we have the same differencing, like the same time series, but we shift it down a little bit, for example, or up. What changes? So it's exactly the same series, but we shifted by a constant up. You see what happens with the original time series. Now there are a lot less observations that are negative in the differencing. It means that there were only 2 periods of decline in the original series. All the rest are positive for sure. And it's growing. It's still a linear growth. It's of course a lot stronger. Why? Because as we just saw, the average level is the summation of the differences divided by the number of time periods, but the number of time periods remains the same. So the summation grew. It means that the growth from the start of the time series to the end is a lot higher when the average level of the difference is higher. And then we start gradually decreasing it. And you see how the trend changes. It is always linear because this is just an integration of stationary first differences. But there are some occasional, more and more occasional declines. The overall growth is less. And when we reach 0, there's almost insignificant growth. It's still growth because this is still positive, even though it's very close to 0, but it is still positive. So there is some minor growth, a lot of declines over the time, and so on. And the second that, not the second, the moment when we switch from positive to negative average level of the mean, the trend changed direction, right? And now it's already an average decline. So these are two very, 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 very similar time series of the first differences. You see, they're almost negligibly different between each other. There is just minor difference in the average, but a crucial difference in the original time series because of the average level and because of the direction of the trend. And similar. So yeah, now when the average is very low, and all of the first differences are below 0, there's just substantial decline every period, but still linear. So this is some important wrap up about the differencing transformations, and we have to finish because I have the makeup exam. Oh, so differencing transformations, they preserve units. That's something that I didn't state before, but it should be quite obvious. So I think it is okay that it appears here. What does it mean? If you consider the original series in megatons, then the differences is also in megatons. Right, so Morocco was emitting so many megatons of carbon dioxide that year, and between those, that quantity changed by so many megatons as well. This is not percentage. This is not something unitless. It's still the same unit, so it's important, and that's why it's also one of the reasons why it's well interpretable and additive. Yeah, and they are very easily interpretable, exactly in the same manner. Sometimes the first differences seem or really are not enough to kill the non-stationarity, and higher orders of differences are to be used. But higher order of differences are very hard to interpret. You saw that second differences we can interpret, but it's already a little bit hard. We can use that logic of differentiation, but this is already like some technicality, and essential meaning is often lost. For second differences, sometimes it's okay. We can still imagine what it means. But for higher order differences, it's already really hard to interpret. That's why some other differences are used. Some other transformations are used. In practice, second order differences sometimes are used when there's no other way. Higher order differences higher than 2 are almost never used in practice in economic analysis. So that's the important takeout about the differences. Next, we would consider percentage change and log differences. I suppose that you are going to talk about them a lot in the practice session this week. And in your empirical exercises about forecasting, I expect you to use not just differencing. Given what I saw from your first reports about your homework assignment, most of you pick the data where differencing will not be enough. Most of you will have to use either percentage change or log differences. So consider that. We are going to talk about them more, of course, because they are very often used in practice, depending on the field, of course, but still. And you will get some asynchronous material about ARIMA. It is important that you consider that asynchronous material for your homework assignment mostly, but also for the next classes. Maybe not as important for the practice class, but for the next lectures it is. So please watch it. Okay, so the presentation is going to be available. Yeah, it is already available. So you can also consider the slides about at least some basic ideas about the transformations, but it is not as important. So if you have now any questions, we have like 4 minutes before I have to switch to the next meeting. And if not, then thank you for coming, and see you next week, hopefully.
By the way, we have discussed log transformations during our practical sessions, and even solved one problem just because we didn't have much material to process.
Yeah, we discussed that with Polina, but we were not sure if it will be possible. Okay, good. So you will continue discussing that, and also you will discuss ARIMA a little bit in the next practice session. I'm not sure when it takes place, this week or next week.
It is placed this week in the timetable.
Okay, I wanted to invite you all to attend the winter school about the master programs, but yeah, okay, so next year, I guess. I thought that there are not supposed to be classes on the day of the winter school, but yeah, okay. So it's your choice anyway. Okay, so no more questions then.
Да, комиссия тут, получается, проходить должна.
Что еще раз? Сейчас мне сложно сразу.
Дани?